Hi everybody, today this lecture is about reflection, refraction, and light waves. Let's get started. So reflection is a process by which a wave is returned into the medium it came out from. So if we look at this is a mirror down here. There's light coming in along the incident ray, it bounces right off, and there's a reflected ray. Applies to any kind of wave, so that could be sound or light or anything. But there's a law of reflection, which is that the angle of incidence here, which is this angle between the normal and the surface of the mirror, this angle, is the same as this angle. That's the law of reflection. Reflection from a smooth surface is called specular. That's like a mirror. Reflection from a rough surface is called diffuse. That's like a glary thing, like on a TV or off a puddle or something. Puddles could actually be specular sometimes, depending on the situation. So if it's like a mirror, that's specular. If it's difficult to get an image, that's diffuse. When a light wave undergoes a specular reflection, its frequency, wavelength, speed stay the same. All right. The law of reflection applies to, we said, all kinds of waves, light and sound included, so C. Light reflecting from a smooth surface undergoes a change in, we said, smooth surface means specular reflection, which means none of these are changed, that's D. Okay, mirrors. There are plane mirrors, which are straight. And the rays reflect off a mirror and appear to be coming from a particular point behind the mirror. So if you have a mirror and you're standing in front of it, you see yourself behind the mirror. Pretty straightforward. This is a virtual image because there's nothing actually there behind the mirror. It looks like something's there, so it's virtual. It's the same size and distance from the mirror as the object. So we all are familiar with mirrors. But if it's a curved mirror, and so this person here, if they have a curved mirror this way, convex, they appear smaller. If it's concave, they appear bigger. So we could curve the mirror in different directions and create distortions in the image. Okay, diffuse reflection. This is when light strikes a rough or regular surface and reflects in many directions. So instead of having the law of reflection, it kind of goes in every kind of direction. Now it could generally go in accordance with the law of reflection. So sometimes you get a sort of image, but most of the time you don't get any image at all. Okay. So rough road surface, because I'm reading the example down here about road surfaces. So rough road surface, because of a diffuse reflection, you see the road ahead of car at night. Wet road surface is smoother because the reflection is less diffuse. It creates more glare. It's more difficult to see. So depending on the surface of the road, and if you have this nice clean surface of water, you might get lots of reflection. If it's just a regular road surface that's dry, you get diffuse reflection, no images. Okay, diffuse reflection occurs when the sizes of surface irregularities are. So if we're going to have diffuse reflection, then the sizes of the irregularities should be large compared with the wavelength of the radiation. If it's small, that's like a mirror. If you polish a mirror, it makes it a little bit better, but the imperfections in the mirror are smaller than the wavelength. So we're going to go with B. Okay. All right, refraction. This is when light bends. So light bends going from one medium to another, and that's called refraction. So here we have this water here and air here. If light comes in, it gets bent when it enters the water. This bending of the path is caused by the change in speed. So the speed of light in water is slower than the speed of light in air, which causes this to bend. So a way to think about this is, if we have train track, these are like train wheels here. And if the wheels go into here, then the slowing down causes this wheel to slow down first. And this one continues on until it hits the grass and continues on at a different angle. So as all the light comes in, as it hits the surface, it turns as the light slows down. Another way to think of this is if you're a lifeguard and you want to get to the person in distress, because we can run faster than we can swim, you spend more time in the sand to run and then go into the water to minimize the amount of swimming you have to do. If you went in a straight line, you'd spend a little bit more time in the water, you'd be slower. So this is light saving time, another way to think of it. So when light enters, well, a fast medium to a slow medium, it takes a bent path because that minimizes time. Okay, so we could think of it as the train track, the train wheel view, or we could think of it as the minimized time view. Either way, when light comes into a medium, it bends. Okay, we're continuing on with the refraction. The speed of light in a vacuum is 300,000 kilometers per second. When light travels through a medium, its speed decreases. As a result of changing speed, when a light ray encounters an interface between two media, it bends. We said that. The amount of bending depends on the relative speed of light in the two media. So if the light slows down more, it's going to bend more. If the light slows down less, there'll be only a slight bending. Light travels slower in glass than in air, so it minimizes the time it spends in the glass. Okay, that's the idea of minimizing the time. Okay, and pathways are reversible for both reflection and refraction. Okay, so here we have light coming in, refracted into the glass, and then when it enters the air again, it goes back into its original direction. Okay, and it looks like here we have light coming in, refracts into the water, bounces off a mirror, angle of incidence equals angle of reflection, bounces off, and then refracts back out. Okay. Continuing with refraction, there's this thing called the index of refraction, which is the speed of light in a vacuum over the speed of light in the material. So a higher n means the speed is slower in the particular medium. So n for a vacuum would be 1, and n for water is like 1.3, and n for air is like 1.0 with a bunch of zeros, and then like a 5 or a 6. So the speed of light in air is very, very close to the speed of light in vacuum. Okay, continuing with refraction. So illusions caused by refraction. So fish might, if we look at the water, the fish may seem closer to the surface because of refraction. There's this bending straw effect, or this like double straw effect because of refraction. Here's a bent pole in water, and here's a beam of light going through something and bending. I guess there's all kinds of effects from this. Refracted light that bends towards the normal and is light that has, so toward the normal, that's this situation. Water is slower, air is faster. Since it's bent toward the normal, it's going to be slowed down. Refracted light that bends away from the normal is light that has, well, let's look at this picture. So when air goes to glass, it bends towards the normal, but when the light leaves the glass and goes to air, it bends away from the normal because it's sped up. So refracted light that bends away is sped up. Okay, dispersion. So speed of light depends on medium and on the frequency and wavelength of the light. So light of different frequency travels at different speeds in medium. So that means red light in water and blue light in water travel at slightly different speeds. Same thing inside glass. So it says blue-violet light travels about 1% slower than red. Because of different speeds, the amount of refraction is slightly different for different colors. And then rainbows are a result of dispersion by many water drops in the air. And this is called, I can't remember. Oh yeah, this is dispersion. Okay, so if we have a prism, we have white light coming in, which is made up of all the frequencies. Because the blue and the red light refract slightly differently, they're going to be refracted slightly differently because they have slightly different speeds, which causes the white light to be split up into the rainbow with blue light down here and red light up here, and this is called dispersion. And same thing happening in the rainbow here. Okay, when white light passes through a prism, green light is bent more than, okay, so let's look at this picture here. Here's blue light bent more than red light. So, and then green light is bent more than red light. Okay, so green light is bent more than red light, but less than blue and violet, so red light. Okay, lenses. There's converging lenses or convex lenses where the light comes in and gets closer. Then there's concave, diverging lenses where the light spreads out. And there's some key features of lenses. We're not going to do these calculations, but if we did do calculations, we'd use the principal axis, which is this line here. Here's the lens. The focal length is a property of the lens that tells you how much the light is for this type of lens, how much it's spreading out, and for this type of lens, how quickly it converges. And then the center of curvature tells us how big these circles on the outside are. Okay, we're not going to use this to do any calculations, but this is how calculations would be done. If we had these properties of the lenses, we could calculate different image distances and we could design glasses. Okay. Here's a pinhole lens. I guess this is a pinhole camera. I'm not sure what to call it. And so if we have an object out here, we can generate an image on the outside here. These are commonly used in all kinds of things like cell phones and security cameras, all kinds of things. Here's a, what is it called? It's a converging lens. And it's instead, the flower is right here. And because the light is refracted in the converging lens, we see a bigger image here. And then we can also take this light here, put it through a converging lens, and we get an image on the wall. And this is real. This is a virtual image because it's not really there. This is the real object. This is the real object. This is a virtual image on the wall. Object's not really there. The action of lenses depend mainly on refraction. Light's bending when it goes into the glass. Huygens principle. Okay. Let's see. I want to focus on this one down here. Every point of a wavefront may be considered the source of secondary wavelets that spread out in all directions with a speed equal to the speed propagation of the waves. So this is it right here. So if we have a source, say we throw a rock into a pond and the wave starts to spread. The way Huygens principle works is that here, if we have a wavefront here, which is like a corresponding wave here in this picture, then each point on the wavefront is the source of a new wave. And if you add it all up, that creates a new wavefront that spreads out further. Okay, and then each one of these points on this new wavefront is a point of a spreading wave, which then if you add it up, moves the wave into the new section. So you get spreading waves. Okay, this is actually a pretty powerful principle. And it explains a lot of wave behavior. Okay, plane waves can be generalized. This is more about Huygens principle. So let's just look at these pictures. This makes sense. So we got waves coming in, and when they come in here, they spread out. So we've got a wavefront. So I'm going to move my mouse along the wavefronts, and then there's this black barrier here and a small opening. When the waves come into the opening, they spread around the opening in all directions, more strongly forward, but also at angles. And because of Huygens principle, we can say each one of these wavefronts is a source of a new wave that explains why it spreads out. If the opening is narrower, we get more spreading. If it's even narrower, we get even more spreading. Okay, diffraction. Oh. Okay, so this is diffraction, what we just described. So diffraction is bending of waves by other means other than reflection and refraction. Okay, so reflection is light coming in and reflecting off. Refraction is light going into a medium and bending. Diffraction is this, where we have an opening or a corner and light or sound can bend around the corner because of Huygens principle. I don't know why they have this picture here. This is a razor blade with light diffracting through around the edges and through the opening in the middle. The superposition interference, which always plays a role, where we can, if you remember that interference, there can be constructive interference where amplitude gets bigger. We can have destructive interference where light can be canceled. And when we have two diffraction sources coming on here, so what this here is, well, let's look at this picture right here. So we got a flashlight on two small slits. These are two diffraction sources that create an interference pattern here of alternating constructive and destructive interference along the screen. This is another image of it. This is the flashlight, white light coming in, two diffraction gaps. And then on the screen, we see, and actually through the medium here, we see points of constructive and destructive interference. The phenomenon of interference occurs for, well, both sound and light. Thin film interference. Okay, so this is if we have a tiny amount of maybe oil on water or soap bubbles here. And this can create interesting interference patterns because of the slightly different ways that the different colors interfere. So if we have a light source up here, so it comes in here, we have glass, we have an air wedge. So in this case, the air wedge is the thin film. And the light comes in, some of it reflects off the bottom, some of it reflects off the glass. And in this case, it's destructive interference, we see nothing. Okay, and depending on exactly how thick that wedge is, sometimes red will be destructively interfered, sometimes blue, sometimes all different colors. So that's why we get to see the colors of the rainbow here. Okay. If a thin film of gasoline was a bit thinner, the wavelength to be canceled would be, well, a bit thinner. Well, if a thin film of gasoline was a bit thinner, the wavelength to be canceled would be probably, so we're talking about thinner. So I think we're talking about shorter wavelengths when it's thinner. Not sure why we're comparing it to blue here. That doesn't really make any sense. But shorter with thinner. If violet light were canceled by the double reflection of sunlight from gasoline on a wet surface, the resulting color would likely be, okay, so if you remember from last time, when we take out, what are we saying? Violet light. We take out violet light from white light, then we need the complementary color is going to show up, which in this case is orange. Okay, polarization. Polarization, so we know that light is a transverse wave, so we can preferentially line up the electric and magnetic fields. So here, this girl here is creating a wave on this string that's oriented vertically, and a wave on this string oriented horizontally. Well, if that's analogous to the electric field in the light, we can orient the light vertically, horizontally, or at any angle we want. So if we have rows of a polarizer and we have unpolarized light coming in all directions, once the light enters and exits the polarizer, all the electric fields will be lined up vertically. If we then send it through a horizontal polarizer, no light will get through. Okay, unpolarized light is light in all directions. Polarized light is light that has gone through a polarizer or is somehow polarized, either vertically, horizontally, or in any direction. Okay, so so we've got some polarizers here. I'm going to focus on this picture at the bottom. When the two polarizers are in the same direction, light is let through both. When the polarizers are one horizontal, one vertical, the unpolarized light goes through one of them, and then it cannot go through the other one. So you get light. In this region, you just get polarized light, either vertically or horizontally. And then in the overlap region here, nothing. If we do it at some angle, then light will be let through. Okay, polarization occurs for waves that are, well, translational. I think that's supposed to be transverse. Longitudinal, A and B. Okay, so I think it's A, but it's got to be transverse, not translational. Okay, do some more questions. Light takes the path from one point to another that is quickest. It takes the quickest time. When light meets a polished reflecting surface, well, it's polished, so all of it reflects. That's not true. It partially reflects. That sounds good. Most of it is absorbed. Maybe not. It refracts, not reflects. I think this one right here. It partly reflects. Okay. Your reflected image in a plane mirror is as far behind the mirror as, well, your distance from the mirror. Okay. To see your full height image in a wall mirror, the minimum height of the mirror should be at least 1/4 your height, half your height, the same height as you, dependent on the distance in front of the mirror. It's got to be half your height, because you only need half the mirror to show the full height, because you're going to be twice as far away. So half your height. The image of yourself in a mirror is actually reversed left to right. Well, it's a mirror image. I'm not sure if that's reversed. Up and down, we're certainly not upside down. front to back. That sounds right. So the back side is now the front side. It reversed. So front to back. Whether a particular, I guess I said that wrong. It's the front side. Front side is pointing that way. In my image in the mirror, the front side is my back side is pointing the other direction. So if I'm looking this way, my image in the mirror is looking the other direction. So front to back has to be reversed. Whether a particular surface acts as a polished reflector or a diffuse reflector depends on the color of the reflected light. Maybe, but probably not. Brightness of the reflected light, that doesn't sound right. Wavelength, that sounds like the best one. Angle, probably not. So wavelength, because the imperfections determine wavelength and the imperfection size determines if it's diffuse or polished, which is why the color is definitely related to wavelength, but I think wavelength is a better answer. Refracted light that bends away from the normal is light that has been sped up. The fastest light inside clear glass is, so the fastest light is the light that will bend the least when it goes into the prism or the glass, which we know blue light gets bent more. So the fastest light has to be red light. When light incident on a prism separates into a spectrum, we call that process none of these. Don't remember the name. It is dispersion. Dispersion. A rainbow is the result of light in raindrops that undergoes reflection, interference, diffraction. No, it's got to be dispersion. A real image can be cast on a screen by a converging lens, diverging lens, either of these, none of these. I think diverging lenses are always virtual images, so converging lenses is the answer. A converging lens can form a real image. We just said that. Oh, either of them, of course, either of these. That's right. It can form either. It's the only one that can form a real image, but it can form both of these. The glasses of a nearsighted person are usually thicker at the, well, I can look at my glasses, and they're definitely thicker around the edges. It's a diverging lens. According to Huygens' principle, every point on a wave is a diffraction source. What do I mean by diffraction? Maybe. Is the superposition of every other wave? That doesn't sound right. Is perpendicular to the rays of the waves? That doesn't sound right. Behaves as a source of new waves. That's the best answer right there. Diffraction is more pronounced for waves passing through small openings. That sounds good. Through large openings? No. From one medium to another? No. From shadow regions? I don't know what that means. So small openings. Diffraction can occur for waves of all kinds. When light undergoes interference, it can sometimes increase in amplitude, cancel completely. Both of them. When light undergoes interference, the quantity most affected is its amplitude. So frequency unaffected, wave nature always there, phase, that's just a shift. It's really just the amplitude, whether it's brighter or not brighter or louder or softer. So amplitude. Interference can be exhibited by sound waves, light waves, standing waves, all waves. Which of these is a property of light waves but not sound waves? So polarization, because sound is a longitudinal wave, it doesn't have polarization. Compared with the individual amplitudes of a pair of waves, the greatest amplitude that can be produced by interference is unlimited. That's not true. No greater than their sum. That sounds good. The square of their sum, half their sum. I think there's no greater than their sum. So it could, if we have two amplitudes, two waves, and they completely add, that would be twice the amplitude. But we can have interference that's anywhere from zero, destructive interference, to twice their amplitude. So it says no greater than their sum, I think is the best. When light waves that are in phase meet, the result is, so in phase means it's going to be constructive interference, which means we're going to have brighter light. A beam of white light that reflects from a pair of closely spaced surfaces has color because some of the reflected light is converted to a different frequency. That's not true. It's deflected. it is deflected, but that's not the reason. Subtracted from the beam, amplified. So it's subtracted from the beam is the best answer. If a portion of a soap bubble in sunlight appears greenish blue, then the light canceled by the interference was, well, it's the complementary color to this, greenish blue. And I don't know what the complementary color is, but I could look it up. I think it's red. Red, okay, good. When light is canceled by the interference in thin films, the color produced is often brighter than the instant light. That can't be right. If it's just subtracting light out, it can't be brighter. Light produces a primary color, well, not necessarily. The complement of the color canceled, that's the right answer. Iridescent, that's a different thing. Polarization can occur when waves of light are undergoing interference. That's not really related. Longitudinal, no, we know that's not true. Aligned, that sounds good. Oscillating at right angles to each other. I think aligned is the best answer. Two Polaroids, one atop the other, with their axes at right angles to each other, whether ideal or not, will transmit. So they're right angles to each other. They're filters for polarization. So that means that 0% will go through. Polaroid that, I think there's words up here. Blank, blank, blank. Polaroid that transmits 40% of instant non-polarized light. Two such Polaroids, one atop the other, with their axes aligned, will transmit. So I can't read the top. I don't know why there's this bug here, but it's probably going to be between 0 and 40%. Let's see what the explanation is. An ideal Polaroid transmits 50% of non-polarized light, which means 100% of the incident light aligned with polarization axis is transmitted. But due to absorption, a Polaroid transmitting 40% means 4/5 of the light aligned with the polarization axis is transmitted. So 4/5 of the 40% that gets through if it gets through both. Okay, I need to read the question more. I still don't understand that. Okay, and that's it. That's the lecture for today. I'll see you guys next time.